Let us continue discussing congruences and its properties. 11th property. Let us take M1, M2, etc. MR be the moduli. So A congruent to B modulo Mi. I runs from 1 to 3 up to R if and only if this A congruent to B modulo M, where M is the least common multiple of, where M is the least common multiple of M1, M2, etc. MR. So this property holds for M. Proof. So to prove the result, we use the property of least common multiple. This is the following. Okay, the least common multiple of any numbers is a divisor of common multiples of that numbers. Okay, or in other words, we write any common multiple of numbers, any common multiple of some integers, some numbers is a multiple of their least common multiple of their least common multiple. Okay, so we prove the result using this property. So proof of 11. So let us assume that A congruent to B modulo Mi, I from 1, 2, 3 up to R. Okay, by the definition of congruence, this Mi divides A minus B for all I from 1 to R. That means that B minus A is a common multiple of M1, M2, etc. MR. So any common multiple is a multiple of least common multiple. Therefore, so M divides B minus A, right? By the recalled result, by the above result. So M divides B minus A. So again, by the definition of A minus B, E minus B. So A congruent to B modulo M. Okay. So conversely, assume that A congruent to B modulo M. Then M divides A minus B. But we know that M is the LCM of, since M is the LCM of MR, Mi. So Mi divides M is a multiple. Just M is a multiple. Okay, so by transitivity of different division, Mi divides M divides A minus B. So this implies Mi divides A minus B. A congruent to B modulo mi. I from 1, 2, etc. R. Okay, so that's a result. The 12th property, it's a very interesting property. If some number C divides A and C divides M, some number divides A and M, and A is congruent to B modulo M. B modulo M. Then A divides one number and it's and the modulus value. Then A divides, sorry, C divides one number and the modulus value, then C divides B. Okay. So proof is very easy just by the definition of congruence property. A congruent to B modulo M implies that M divides A minus B, which implies there is a Z integer such that A minus B is equal to MZ. Okay, so here B is written as A minus MZ. Since C divides A and C divides M, so C divides A minus MZ, linear combination of A and M. So A minus MZ is nothing but B, so C divides B. Okay. Then 13th result using the 12th property. If A congruent to B modulo M, then A and B have same GCD with M. Okay, GCD of A and M is same as B comma M. Okay. So let's take D equal to A comma M and G equal to B comma M. So we have to prove that G equal to D. Right? So we use the previous property since given that we have assumed that D divides A comma M. So D divides A and D divides M. Right? By 12, we write that D divides B. Right? Which implies that already D divides A and D divides B. So D is a D divides M and D divides B, which means that D is a common divisor of M and B, but G is the greatest common divisor of M and B. So G is the greatest. Okay, and also G divides B and G divides M, which implies that G divides A by property 12. By 12. The 12 says if a number and is not okay, and the moduli are divisible by a common number, then the other number in the congruence is divisible by the common number. But D is the greatest common divisor, so D is bigger. Now, from this both, you get G equal to D. Therefore, A comma M equal to B comma M.